Keeping warm in the frigid winters of Baltimore. Heat of reaction of various dissociations for ionic compounds and the creation of heat packs. In the frigid winters of Baltimore, there lacks a convenient source of heat to keep us warm. To make an appropriate source of heat, we decided to create a portable heat-releasing reaction with distilled water and different ionic compounds that are present around lab. We will investigate this issue as a calorimetry experiment, seeing which dissociation produces the biggest temperature change per unit cost. During reactions, chemical bonds are broken and formed. Energy is absorbed when bonds break, and energy is released when bonds are formed. The formation of bonds is exothermic, and heat is released. In this calorimetry experiment, the heat and temperature gained will be based on the heat capacity of water, the amount of heat required to raise 1 gram of water 1 degree Celsius. When ionic compounds dissolve in water, the bonds between the ions of the salt are broken. When the energy needed to break bonds between ions is less than the energy released during the formation of new attractions between the ions and water molecules, the overall process of dissolving the salt results in the release of energy in the form of heat. Here are some of the variables in the reaction. Our independent variables were the type of substance. We used 5 different ones. The dependent variables are the final temperature that these reactions produced. The control variables are the amount of moles of each substance, the initial temperature, and the amount of distilled water. Here are the substances we used: lithium chloride, calcium chloride, sodium carbonate, sodium acetate, and magnesium sulfate. We also used distilled water, a temperature probe, LabQuest number 35, a calorimeter, which was constructed from a styrofoam cup with a styrofoam top, a stirring/heat plate, and a stir bar. The experiment procedure was as follows: 0.05 moles of each compound measured out using analytical balance. Calorimetry experiment set up using 2 holiday-themed styrofoam cups from Dunkin' Donuts with the styrofoam top used above to contain that heat, a temperature probe, and a LabQuest computer. This was set on a stirring plate with a stir bar added. 100 milliliters of distilled water was added to the calorimeter with the substance added shortly after. The LabQuest started recording data immediately after. The data was measured for 600 seconds. The procedures above were repeated for all 5 compounds. In order to obtain the same molarity for each solution, we needed to convert our moles of compound to grams. The chart is below. Here is the setup for our calorimetry experiment. Here are some of the equations we used to do our calculations. These are some of the calculations that we ran after lab. Here you can see the cost in dollars per kilojoules of heat generated is the least for CaCl2, coming to about 23 cents per kilojoule. Here are some of the data that we gathered during lab. Note that magnesium sulfate had the greatest stabilizing temperature, but it was not the cheapest per kilojoule of heat generated. Some of the errors that we noticed were that the calorimeter top did not perfectly isolate the system from the universe, so some heat would have been lost to the surroundings. Therefore, the entirety of our data would be skewed to the left. Unless we have a better calorimeter, this error is difficult to account for. A random error is, when utilizing the temperature probe, the temperature obtained can vary around the actual temperature. For our analysis, we searched the cost of each compound for 500 grams and then calculated each compound per mole. We then calculated the cost per change in temperature and determined that CaCl2 is the most cost-effective per change in temperature. Here is a graph of our change in temperature over time. As you can see, magnesium sulfate is at the top, calcium chloride second most, and everything else towards the bottom. Here we see the construction of our heat pack. It involves 2 Ziploc bags with one put inside another. The inner bag contains water, and the outer bag contains the CaCl2, which we decided to use for the official application. Here we have a cold boramate. Watch as Kiefer comes to save the day with his heat pack. Through a combination of squeezing and tilting, the reaction is initiated. Here are some final observations. The bag warmed up greatly where the ionic compound was located once it came in contact with the water. Unfortunately, the heat did not last as long as we would have liked, but the bag certainly reached a high peak temperature. If we could maybe create a mechanism that sustains the peak temperature for a longer amount of time, we could have a heat pack that is more competitive in today's markets.